Hello everyone, welcome back to the episode 6 of our high level system design playlist. And in this episode, we will take a look at the database choice and how to go about designing databases in real life production scenarios and in design challenges. So let us start with this episode. So in this episode, we will see that how we can design databases, right, that go from a prototype level to production level. We will see the journey that it makes and how that is made possible. Okay, so the structure of this video will be like we will start. So there will be four parts. In first part we will see the SQL versus NoSQL versus key value and versus hybrid. So the various approaches that we have for database choice, right? And then after we are clear with this, we will see that how in real life scenarios we go about data modeling process and how we build and structure our data in a system. Then we will see that what are the scaling strategies we follow for scaling a system and its data from a prototype level to a production level. So this will be the third part of our video today. And then finally we will move to the fourth part where we will see some real world data design patterns and best practices. Okay, so this is the approach that I am trying to follow today, and hope that this will give you a structured roadmap to design databases in a design challenge or in a real life scenario. Okay, so let's start with this. So we will take the first point, that is database types and choices. Okay, so to understand this better, we will look at two core database design properties, that is acid and base. Okay, so acid and base, these are two contradictory words, and these very well defined the database properties that are on offer. So acid, as you would know, is an acronym that defines four core database properties. So A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. Correct? We will take a look at this one by one. Similarly, when you talk about base, we have, it is also an acronym that characterizes the important properties of a database. So first one is base databases are basically available, right? And then they are soft state databases, which we will see what we mean by this. And then the third point is they are eventually consistent databases. Okay, now let us see what we mean by acid properties of a database. So first I'll touch them briefly so that we don't spend much time here. So first, atomicity. This means that a transaction on a database either completes entirely or it fails entirely. It does not stay in a middle, or it does not end abruptly in the middle. Either it has to complete or it has to fail. Okay. Then we move on to consistency. Consistency means that the database will remain in a valid state throughout the transaction. Okay. So let's say if a transaction starts here and goes to 2. Okay, so in between the state of the database won't be corrupted. That is, till the point, from the point that 1 started executing and before it reached 2, all the reads on this database will get you 1. Okay, you will get a consistent value, and it will not be the case that, okay, if there are 2 read requests, then one read request gets you 1 and the other one gets you 2. That won't be the case. All the read requests till the transaction is committed will give you a consistent value of 1. So this is the part of consistency. Now we move on to isolation. So isolation property says that all concurrent transactions do not interfere with each other. Let's say we have a transaction T1 and a transaction T2 that are running on a database. T1 started at time T1, T2 started at time T2. These transactions run as if they are running in their own isolated environments, and they don't interfere with each other's resources. In case of resource contention, there are database properties by which they resolve the resource contention scenarios, but uh, overall they do not interfere with each other. Okay, now we move on to durability. Durability means that all the committed transactions of a database should stand any system failure. Okay, if it is a physical or a natural disaster, the database server is burnt or something, we are not guaranteeing on that, but committed transactions should always survive any technical failure, and whenever the database is back up, the committed transaction should be restored. Okay, now let's move on to see that what we mean by base properties. So base means, first point is basically available. Okay, so base databases guarantee that the systems are generally available all the time. Generally available. Okay. Then it says that it is a soft state database. That means the data consistency is not guaranteed in these types of database. Okay. And they what they do is, what they guarantee you is that you will have eventually consistent data, but not like high levels of consistency. This is offered by acid, but bases tell that okay, you can read bulk data from me, but I'll guarantee you that I'll provide you some data, but I'll not give the guarantee that the data is always latest. Correct. So this is basically what is the two types of database that we have, that is acid and base. Okay. So the examples of acid database, as you might be knowing, is a very famous one is PostgreSQL, and an example of base database might be a more document based database like a MongoDB. So these databases are used when you need extremely high levels of consistency. Okay, this is the primary factor. For example, in financial systems, correct? And these databases are mainly used in, let's say, social media use cases, where you are fetching the number of likes on a post. So if one like or two likes are not synced immediately, then it won't be like your system is broken, right? But if a $5 credit is not done immediately, then it means that it's a failure on part of the bank or the financial institution. So that's why it is very important, right? Now we will see that what are the basic. So now, having seen the properties of the database, we will see that what approaches we can take to achieve these properties inside a database, and what kinds of approaches are there. So primarily we will come across these things that I'm going to tell you. So you will come across primarily with a with a SQL DB. You will also see a NoSQL DB. You will also see a key value database. Okay. And generally in real life production scenarios, we will also see hybrid databases, which we will see what's that. So first one is SQL database. So what are SQL databases, right? So SQL databases basically, they are structured data which have predefined schemas, right? SQL databases are structured data which have predefined schemas. Okay, and they are these SQL databases are very useful for scenarios where we have complex queries with multiple joins in the system. Okay, why? Because the table is because the data is structured in the form of tables, and that's why there is a concept of primary key and foreign key. And using these concepts, it is very useful in scenarios where the system involves complex queries with joins. Okay. Also, one major property of SQL databases is strongly acid compliance. Strongly acid compliance. The SQL databases will guarantee you strong acid compliance, and they, as an effect of this, they will provide you strong consistency. Okay, and that is why these databases are highly preferred in financial systems where the recent and the most upgraded data is required. SQL databases also have very mature ecosystem, and the tooling and the support for these SQL DBs are quite extensive. Okay, so that is one more important why you will see SQL databases being used so much. And these are, like I said, these are mainly used for financial data user management. Let's say you have complex analytics, and you want to run queries with joins, and you also have some regulatory compliances, right, for which you need good auditing tools on the database. For satisfying these requirements, SQL databases is very good. Okay, then we go to NoSQL database. So NoSQL database has a flexible schema. Okay, in a SQL database, you will define the structure of the data at the inception stage, but in NoSQL database there is no fixed structure to your data. Okay, so it's a document based storage. Okay, the files or the data that you store in a NoSQL DB are stored as documents that are similar to JSON, a JSON format, correct? And this does not support complex joins. You can do simpler joins, but if your object structure is nested, and then it does not make sense for NoSQL databases to provide the feature of complex joins, because that makes the system quite inefficient. Okay, NoSQL databases are very helpful when your system needs high amount of horizontal scaling. That is, the read or write request on your system is huge, and you need to serve a huge amount of data. In those scenarios, NoSQL DB makes very much sense. NoSQL databases also make sense when your system hints towards eventual consistency. Okay, when not showing the data, not showing the most updated data does not hurt your business process. In those scenarios, NoSQL data is the most useful one. For example, in social medias, correct? In social medias, in likes and the comments on the post, and all similar scenarios, you'll see that NoSQL databases are the best choice, because even if you do not show one or two most recent likes or comments, it won't hurt the system bad. So NoSQL DBs are mostly used where there is very high throughput or huge amount of concurrent access on your system. For example, social media. Okay. Now we move to the third type of storage, that is key value storage. Okay. So key value storage is a special type of storage that provides you with very fast reads, ultra fast reads. Correct. So the data is stored as simple key value pairs, and it provides you the ability of ultra fast reads. Okay. So because the data is not stored in a sort of physical hard disk, rather key value storage are mainly in memory storage. So the traversal time of the data, the to and fro traversal time, is greatly reduced, and because of that, it can provide you microsecond response times, and that forms a very good use case for using this as a caching DB. Okay, and key value stores, as the implementations are, let's say DynamoDB or Redis, they already have, for because of this they have already have caching capabilities built in. By caching capabilities, I mean methods like get, put, delete, and so on. These key value pairs have a very predictable performance, right? Because they are simple key value pairs, that are just being stored in memory and not on physical solid state drives, correct? But one thing to note is key value storages are quite costly, so you want to be using these very efficiently, and you want to be using proper caching algorithms which can improve your cache hit ratio, so that you only store what you must need, that you require very much, that are very much hot data in your system. You store only those keys in your system. So these are perfect for caching. Also, session storage will make a very good use case, shopping carts, some real-time features, and so on. Now we'll move to the final strategy in design database choice, that is a hybrid architecture, which you will see being used in most of the production systems. Why? Because this gets the best of all worlds, right? So based on our use case, based on the system requirements, what we do is we break down the systems. Okay, we break down the system. Let's say the user and the profile data, because it requires high consistency, we go for SQL databases. Let's say for likes, if your system is working with likes or comments, you store this part in a NoSQL DB. Okay, and let's say your user authentication session you store in your cache, that is a key value pair support, key value DB supported by Redis, right? And in this way, specific to the use case, you can implement whatever database is required, correct? And let's say if we require some analytics data, we can we can use something like Cassandra. So this is a sort of hybrid approach, where based on what the use case is, we are just trying to figure out the perfect fit for each use case, and based on that we design our databases. So this is good for complex applications where there are multiple data patterns, and this is generally seen at enterprise scale. Now, having seen that, okay, what are the types of database and what are the strategies related to them, how do we choose now? Like whenever we see a system, or whenever we are in a situation where we have to design a database for a system, how do we choose the right database for a system? So for that, let us take a look at our database design choice framework. Okay, so this is a very simple mental model that will help you think in the right direction, and based on four important properties, we can arrive at a good decision for our system. So first factor is, what is the consistency requirement for our system? Okay, this is the first factor. Then we see that what is the query complexity of our system. Okay, once we are done with once we know that what's the consistency requirement and how complex are our queries, we move ahead and we think in terms of what are the sort of what are the team comfort levels. So we are working with a team, right? So what is the opinion of our team, and how they sort of view the difference, what is the comfort level with each one, correct? And based on that, that also plays an important factor. And the final one is scale and performance. Okay, so based on our scale and based on our users, how will the database scale and how will it perform, and that forms one of the you know guiding principles for choosing a good database. So first one is consistency requirement, right? So consistency requirement, what will it deal with it? Let's say it will ask that what is the consistency level of different components in our system, of different components, correct? For example, user and profile data need very high consistency, okay? And let's say we are working with comments or likes, you know, so these can require, we can have eventual consistency on these, correct? Then API keys, or let's say the paste ownership. Let's say we are building a paste bin system, that is our CodeShare, and whenever we paste something, what whether we are authenticated or not, who is owning the paste, for that we require high consistency, correct? So login logout functionality, okay, login logout, all these requires very high consistency, correct? And let's say we have view counts again on our paste counts, correct? This we can live with eventual consistency. So based on this gives us an idea that okay, we have to go for majorly we need very high consistency in most of our use cases, correct? Then we come to query complexity. So next one is query complexity. Okay, so this one basically, let's say we have some scenarios like we want to show all the public posts by a user, okay, in an organization, let's say. So this becomes a little complex query, correct? Because we have to fetch all the users in an org. Then for that user, we have to get all their public posts. So this becomes a complex query where we are saying joins from multiple tables, and this hints us toward what? SQL. Similarly, we can have simple queries as well. We can have, let's say, get all posts by user by a user. This can be a simple query. So for the posts, we don't need an SQL. We can go for a document-based storage as well. So it can be a hybrid approach. And let's say we need some analytics, correct? So the analytics teams and reporting team wants us to provide some reports, and they again result in a complex aggregation. This again points to SQL, correct? So this is the query complexity part of it. Then comes the third factor, that is scale and performance. So for CodeShare, what was our scale? We have 10 million pages per day, correct? So in this scenario, we see that there is a high read to write ratio. So since there is a high read to write ratio, we can use global CDN, correct? Global CDN will incorporate caching, okay? And if we incorporate global CDN in caching, we can go for around 100 milliseconds of response times, correct? So this hints us towards that okay, for caching and for caching requirements, since we have a high read to write ratio, we will go for a global CDN with caching, okay? Then the fourth point hints us towards what is the team preference and operational factor, okay? So let's say if the team has Postgres experience, prior Postgres experience that most of the teams in today's industry have, and if the team needs manual monitoring tools, this can be easily provided by Postgres or SQL databases because they have a good community of tools and all. And let's say we have audit compliance audit compliance, regulatory compliance requirements. For that, the SQL databases makes most like the best choice, right? So the point that I'm trying to highlight here is we do not go for the best database for all scenarios, correct? There can't be a best database that can fit every scenario, right? But rather we always try to go for the right database based on the use case. What the use case is, based on that we'll go, correct? So for CodeShare, as of now, I am saying that SQL databases make much more sense because of all these factors that we discussed, okay? So now that we're clear that okay, we will be going with SQL databases. Now let us deep dive into actually designing this data model. So we will see how we can design the actual data model in the uh, our code space app, okay? So for this, what we'll do is, for this we generally create entity relationships in our system, okay? This again becomes a part of low level system design, but I think we'll have a walkthrough over it. So what it will be is like, what are the entities that you can imagine it? So first thing, we can have a user, correct? Then what we can have, what is a fundamental entity in our system? We can have a paste, correct, that the user can create. Okay, then okay, so let's start with designing these two, the user and the paste. So let me just bring in this SQL table creation script, and we will take a look at that. So here you can see that this is our table creation script. Okay, so we have created the table users with these fields, and notice that we are making some very important design decisions here. So what are the design decisions that we are making? Okay, so first one is, we are using a universally unique identifier, or UUID, versus auto increment, correct? So why we are doing this? Using a UUID will safeguard our system in a distributed environment, and when the system scales to a lot of when it's deployed across regions on a lot of computes, the UUID will make us scale proof. So that's the idea here. Then I think you'll notice that we have separated the email and the username fields, correct? So separation of email and username. So this will again help us provide sort of unique and not null identifiers for our system. Next, we have enum for our account type. We have the enum for our account type. So what this enables us to do is, we have control vocabularies for type safety, and we can provide clear business rules. We can control what are the fields that are being provided here, and we can use the database to enforce some valid values. The fourth point to see here is, we have incorporated password hash, correct? So this is very useful for security features. See, so at this level, you see, even at a very low level of a table creation script, we are making so many design choices. So high level system design is a process that should be inculcated right into your sort of even each and every step of your SDLC. Now let's say we move on to our second entity that we have, that is paste. So if we take a look at the paste table creation script, we will see that we have made many interesting design choices here as well. So if you see in this script, there are again few design choices. So what we have done is, we have inculcated a separate short ID field, correct? Because there will be unique URLs generated for our paste, that will be the short URLs, and we can store it here. Yeah, similarly we have a nullable ID field, that is org ID. This helps us in creating non-required dependencies to other tables, correct? Then we have a visibility enum. We have a visibility enum that again helps us to establish good grammar in the system and clear business rules. Then we have a expires at. Okay, we have an expires at, which is again nullable. What does this signify? This signifies that posts can even not expire, correct? There can be some posts can never expire, or they can be alive forever. So these are the key design decisions that even our table creation scripts at database level can drive. And the point to take away basically from this is, every field in our DB design has architectural implications, correct? Every field is important, and how we are using and exposing every field is very important. Okay, and this, the way we have used UUID, this can help us in future sharding when our system scales, correct? And the concept of nullable foreign keys, they can help us to create optional relationships, right? We saw that they can help us to create optional relationships. And then we have the enums that incorporate type safety and business safety rules, correct? Now, having seen this, let us see how we scale our database system from a prototype to production level. How to scale, correct? So let us look at phase one. So in phase one, what do we have? In phase one, we have, let's say we have an app server. So this is our app server, and this is talking to our database, that we have a single instance Postgres database, correct? So this is useful when we have low traffic, we are in an inception phase, and when our deployment is quite simple, correct? We don't have a Dockerized or a Kubernetes based clusterized deployment that's being deployed across multiple regions, and this is this is very much cost effective. Okay, when does it break? It breaks once the traffic increases. It breaks once your traffic increases. So for the improving this, what do? We apply the principles that we have learned. So we move to phase 2 of our database design. Phase 2. What does phase 2 say? Okay, so in phase 1 we had 0 to 10k users. Now in phase 2 we are scaling from 10k to 100k users. So as we are scaling from 10k to 100k users, like our system is moving towards a read heavy pattern. We are experiencing more reads on our system, that is more people will read the pastes, correct? So what we'll do is, let's say we had our app server, right? Let me just get this straight. So we have our app server, and this app server talks to our database, right? So this is our Postgres. Now what we'll do, we'll introduce the concept of read replicas in our system. So what will happen is, all the read activities, we will buy or we will have 4 more database servers, R1, R2, R3, R4. These will be read replicas and will be synced with our main or the master DB, correct? So what will happen? All the traffic, read traffic that comes from the app server will be served by our read replicas, and the write traffic will be served by our master database. So let's say we have one app server, right? Similarly, if the load increases, if we want to have one more app server, this can also talk to this read replica. And if the load further increases, if we want to have one more app server, this can also talk to this read replica, right? In this way, introducing the read replica can help scale our system. So what are the pros in this? So we now have a scaled read capacity, okay? And also what we have a, let's say when we will go for read replica creation of our database, okay, we will have a geographical distribution of our data, correct? So app server 1 will talk to its nearest DB, app server 2 will talk to its nearest read replica, correct? Okay, as we know, pros always comes with some cons. So what are some cons here? We observe that there is some replication lag whenever the data is syncing to the master, right? So the read replica and the master's data, they have to be in sync. So this syncing sometimes creates some lag, okay? And of course, as we are introducing more components in the system, we are increasing the complexity in the application logic, in this case in our DB app logic. Okay, so now we were in the phase 3 and CodeShare was working good and we were able to serve 10k to 100k users. Now our business grows even more and we have to improve our system further to support even more scale, correct? When this is the scenario, we move to phase 3 of our database design. In phase 3, what do? In phase 3, the traffic that we are experiencing or expecting is 100k plus users, right? So once we have 100k plus users, the strategy that we will take is, earlier we were having one master database, correct? Now what we'll do, we'll create as one master database is not able to serve 100k plus users, we will go for a technique called horizontal sharding of the data, correct? So we'll go for the technique of horizontal sharding. What is this term? This is nothing but we'll split the master database into 2 or 3 separate database instances, correct? Now what we'll do, so we'll have a primary master. We had a primary master rather. So this was our primary master. Now what we did, we split it up. So let's say we created from one primary master, we created 3. Let's say we had 0 to 600 IDs here, correct? So when we split, this will contain 0 to 200, this will contain 201 to 400, and this will contain 401 to 600, correct? Now once we have this, so we create 3 new master database. This is M1, M2, M3, and as we had in our previous strategies, we already have the read replicas that are attached to all these 3, correct? So let's say if we copy this, M2 gets its own read replicas and M3 gets its own read replicas. Okay, now the system is set up. Now because our primary master is split into 3 masters, 3 new master database instances, what we have done here is we have done sharding and we have split it based on some key, right? So let's say for example, in our case the key was user ID. So this user ID is called the shard key. This becomes the base of splitting, okay? So what we did in phase 3, to serve more users, we we increased our master database number of master databases by horizontally scaling our master database, or horizontally splitting our master database. That is called horizontal sharding. And horizontal sharding is done based on a shard key, and shard key is the unique parameter based on which you split your database. Okay, so now let's say we have multiple app servers here, right? We have app server 1, we have app server 2. So each app server can now independently talk to its read replicas for read purpose, and also to write master databases for writing. So now we are good, and in phase 3 we were able to serve 100k plus users. And in this, what did we achieve? So we had some pros, right? So we scaled both reads and writes, correct? But again, we also had some cons. What were the cons? So now let's say we split our master data into 3. So there now comes the problem of cross shard queries, which is a big problem. Okay. Also, whenever we are splitting, we split based on user ID, right? Let's say after 10 days, 100 of our users logged out of the system, and we have to delete their user IDs from this. So in that case, we have to perform rebalancing of the keys, and rebalancing of the keys becomes quite inefficient because all the data has to move from one system to another. Okay, and this increases the complexity in the system. Correct. So for solving this problem, there is a concept of consistent hashing, which we will see later. Okay, so now we are at a stage where our phase 3 is quite stable, and we are nicely serving 100k plus users. But now we need further improvement as our business is even growing more. So now in the phase 4, we have to support a lot of users, that is 1 million plus users. And in this scenario, we have nothing but we have the choice to go for a hybrid approach, which is also the approach that you will find in most enterprises. Okay, so in the hybrid approach, as the name suggests, we will go for a SQL plus NoSQL combination. Correct. So let's say in this, what we'll do is, for the user data, we can go for SQL databases, right? In which we will store the auth data, we can store the profile data, and etc. That requires very strong consistency, right? For the paste content, right? For the paste content, as the paste content will be unstructured, and there will be huge amount of read volume on the paste content, correct? So paste content will be unstructured plus read heavy, and of course these two things hint you to use NoSQL solution for storing our paste data. Okay, in our case we can use MongoDB for this, and for SQL we can use Postgres. Okay, now let's say we want to save session IDs, okay, login info, and user temporary user content, stuff like this. For this, automatically our choice becomes we have to go for caching, correct? And hence we use a key value DB like Redis. So this is how in production scenarios a hybrid approach is taken and it is implemented, correct? So this is what did we accomplish here? We have optimized our DB by use case. Whichever use case we have, accordingly we are using this type of database. One challenge that we'll face here again is we will have multiple systems to manage. So we have to weigh in the benefits of using this system, introducing these systems, and if it benefits our system, we'll of course take it. Then we have data consistency problems. Okay, because all these we are using 3 types of databases that guarantee you different types of consistency levels. So that expectation needs to be set at the onset, correct? So what did we do? We started from a very basic thing, that is a single DB instance. Okay, in our day 1 or phase 1. In phase 1 we started with single DB instance. Then in phase 2, as the scale increases, we implemented read replicas, correct? This was in our phase 2. In our phase 3, the scale increased even more, so we had to introduce the horizontal sharding, where we sharded our master database into 3 databases so that we can scale both the reads and writes. After that, once the scale crossed 1 million users, we had to go for a hybrid setup, and which was based on the use case that we were working with. So in this way, in 4 phases, we were able to scale our CodeShare system from a prototype to production. So the simple funda here is, what did we do? We started simple and we evolved systematically, correct? Whatever the system required us to do at every phase, we did that, and that's why we were successful. Okay, now we'll see some real life examples from the industry that will help you relate to these choices. Okay. For example, when we talk of Netflix, correct? So Netflix, what's their requirement, right? They have viewing data, and they will have, let's say, viewing history, correct? They will have viewing data, they will have viewing history, and the write volumes are very high. The write volumes are extremely high. Why? Because every time a user views a web series or some movie, the viewing history has to be updated, the view data has to be updated, the recommendations have to be sent in, right? But the thing is, even if you don't send a recommendation immediately on other devices, Netflix is good with that, as their business is not impacted. So Netflix is good with eventual consistency. Now you see the pattern, right? They are having high write volumes, they are good with eventual consistency, right? And one more thing is their data is not geographically distributed, correct? They are all over the world, and their data has to be present at the nearest servers that are to the users. So in this case, what is the database strategy that Netflix took? They went for a multi-data center, where they went with Cassandra clusters. Okay, they went for the document based choice because that is what satisfies their needs. Okay, so it provided them with denormalized data that was very essential for their fast lookups and their requirements. Correct. Next, we'll see the example of a payment processing system called Stripe. Okay, so at Stripe, again, this is a financial system. So already you might have guessed it, right? So they need very strong ASIC performance. Correct. They have again complex queries with joins. Okay, they have strong regulatory requirements because they have to provide, and hence they have to provide audit trails to their data. Okay, because they're a financial company, and they have strong regulatory requirements. Okay, so all these, and they need a very very high level of consistency. So all this needs to work SQL for them. Correct. So they went with a region based SQL implementation. So let's say they have one database server in EMER, they have one in Europe, they have one in APAC, and let's say these are their master databases which supports writes, and attached to these are their read replicas. These are the read replicas, and this is sort of a high level view of the Stripes database setup. Okay, so with this we come to the end of this episode, and I hope this episode made sense for you and it added value to your time. And the core of this episode is that when we when we do architecture for database, and when we scale it from prototype to production, we have to follow a very simple funda, that is we have to start simple and we have to evolve systematically based on what the system is asking us to do. Okay, so great database architecture balances the current needs with future growth. I hope you find this video useful, and we will meet again in the next episode. Thank you.